Hello there. Welcome to the Practical Electronics channel. Before we get into today's designs, let's take a moment to highlight the objective of this channel. Now, this channel lays particular emphasis on personal practical circuit design, sometimes breaking away from the status quo, without ignoring those theories relating to our designs. So whether you are in academia or on the job, this channel has pretty much got your back. Now to today's lesson. Now in the starter video, you saw a motor whose speed was controlled sympathetically with the brightness of an LED. The motor sped up and slowed down while the LED set glowed and dimmed simultaneously. And you ask, what possibly could be controlling these two devices? Your guess is as good as mine. It's a resistor. To be precise, a variable resistor. Resistors come in different shapes and forms. We have, for instance, a dropper resistor. This is about 5 watts. It can support circuits that dissipate a whole lot of power. So this is a dropper resistor. That is a popular name. We even have a potentiometer. The potentiometer I have in my hand is a 50 kilo ohm potentiometer. It is a kind of resistor too. We have our everyday standard resistors. We even have wire wound resistors, light dependent resistors, among others. But the closest resistor to home with which we implemented this circuit is probably lying around in your study room. Yes, a pencil. I have in my hand a pencil which has been ripped apart, where the graphite, the inner graphite, has been carefully taken out. So you notice that the graphite is continuous. Let me make it clearer for you. I had a pencil like this. I ripped it apart patiently so that in the end, I was able to have access to the writing matter, the graphite, ingrained in the circuit in a continuous fashion. So this graphite is not broken. If you want this circuit to work to your satisfaction, you need a graphite very continuous. So grab a couple of pencils, keep working at it, till you have a continuous layer of graphite. So that was what was serving as our variable resistor. For instance, I have my multimeter with me here. I have powered it up. You notice that currently it has been tuned to the voltage reading, but that is what we want to measure. We want to measure the resistance of the graphite. So I switch it to the resistance range. I'm not expecting something beyond 200 ohms. Okay, so that's where I've set it. Now let's keep an eye on the meter as I measure the resistance of the graphite. So here we go. Right now we are having a reading of around 30 something ohms. Let's see what becomes of the resistance as it appears on the resistance meter, ohmmeter, as I draw the leads close to each other. So watch. As the leads got closer, the resistance has reduced to less than 20. Let's take it even closer. It's now reading about 12. Even more closer, we have 10. I also used a power pack. Let's check the voltage quickly. So right now, I'm going to switch the multimeter to the voltage gauge. So it's now on the voltage gauge. Let's measure quickly how much voltage I have in my power pack. So this is one lead of the power pack. This is the other lead of the power pack. According to the reading, it's about 5.7. You notice that both terminals of my power packs are green. So for purposes of differentiation, I have tied a knot on the positive terminal. Very well. All these components I showed you were wired with the help of a breadboard. This is a breadboard. I'll show you it has nothing to do with bread. So if you don't like the name breadboard, you could call it project board. It doesn't matter what you call it. Your circuit will still work fine. This is the back of the breadboard. Let's take a moment to go through the inner workings of the breadboard. Now, you notice that there's a continuous stripe of metal from here to here. And then there's a brick. Just to make sure you see the brick properly here. Notice that the metal strip breaks here, and then it is reintroduced here to the end. There's another strip on the side. But there is separation between the strip here and the strip here. So they are not joined together. So from here to here is continuous. This one is separate from this one. There's a break in that order. And it happens on the other side of the breadboard as well. So what is happening here is replicated here on the other side of the breadboard. So what it means to the front end of the breadboard is all these holes here up to here, they are the same. And then from here to here, they are the same. This is the brick column I spoke to you earlier, which means from here to here are the same. From here to here are also the same. The logic is replicated on the other side of the breadboard. Okay, let's go to the back end again. So while these long metal strips are horizontal, these ones are vertically aligned. So notice here, here, here. So this is continuous, separate and different from this one, which is also continuous. This one is just as different from this one. So this one is a metal strip on its own. This is an independent one, another independent one, another independent one, and it extends to the last metal strip. There's a break in between, and the logic is repeated here. What it means to the front end of the breadboard is that these lines are the same, these ones are the same, these ones are the same. This is the break I alluded to here. And then the same thing is done here, 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 here. So that is how the breadboard operates. Now, let's see how the circuit was wired up with the aid of a breadboard. I have the breadboard, which I introduced you to. I have my DC motor here. So I have my positive terminal running here along this line. And because there's a space between here, I have put a jumper to link this line to this line, which means the line has become continuous from here through to the end here, courtesy this jumper. I have repeated the same on this side. The space here has been linked by a jumper cable here, so that this line starting from here to this end becomes continuous. So this will be my positive terminal, and this will be my negative terminal. So let's do this. I have the negative terminal connected via breadboard. And this is the LED set we used. I'm putting it here. So the terminals of the. So let's put this one here. Okay. Now I did mention that these two devices are connected in parallel. What it means is that the negative terminal of the DC motor was tied to the negative terminal of the LED set, while the positive terminal of the DC motor was tied to the positive terminal of the LED set. My apologies. This way. Okay. I have this one also here. Okay. So wired up in parallel. Good. Now this is our power source. You remember I did mention that there's a knot on the positive terminal here. So it means our positive terminal goes here. And this is our negative terminal. We could put the negative terminal inside this and everything just starts. But that's not what we want. We want to be able to vary the speed of the motor and the brightness of the LED. So I have my homemade resistor here. I'm going to insert it in series with the circuit. This is one of the terminals. This one cannot, if you look at it, this is a soft wire. It will not fit into the holes in the LED board. So let me attach a jumper cable before I insert it in. So I'm tying it this way. Notice how I'm tying it. So here we go. I put it inside. Good, this way. So now, this will be the other end with which I regulate the speed of the motor and the brightness of the LED. Let's see how it works. Here we go. Let's get it closer and see what it becomes. Watch the LED, the contact is breaking here. This contact is not a very good contact. So let's do it well again. Let's see. Yeah. Now let me swipe it closer. Do you see? As it gets even closer, let's come back a bit. Okay, let's do it one more time. Good. So this is what you saw in the starter video. As I pull away, the speed reduces and the LED dims. Let's get closer and see. Okay. But you see, this homemade graphite resistor cannot be your everyday resistor. One, it is very bulky and it is very fragile. If not handled properly, to just fall to pieces. So I'm going to set this aside. And instead, we'll deploy this resistor. It's 50K potentiometer. This is what we're going to use. Notice how it has 3 legs, but I'm relying on only 2, this and this. I could use this and that and achieve the same results. But what is important here is that I'm using only 2 legs of the potentiometer. Now let's wire it up. So you see my jumper cable here. Here. The jumper cable. I'm going to, you notice that it renders these 2 sections continuous. Now instead of the jumper cable, I'm going to put the potentiometer there so that we're able to vary the current running through the circuit, by which way will regulate the speed of the DC motor and the brightness of the LED. So instead of the jumper, I'm going to insert the potentiometer here. Okay. So we have this. Yeah. Yeah. Okay. Now let's power it up and see how it behaves. There you have it. Let's see. So notice how I'm able to control the speed. You know, it is a 50 kilo ohm potentiometer, surprisingly difficult to control because the list I make injects a very high resistance into the circuit. So I have to control it carefully in small things. You see what I'm talking about? So if you want to make the control of these 2 devices a breeze, you should reach for a 1 kilo ohm potentiometer or a 500 ohm potentiometer. It will make the control much easier. So you get the concept. Okay. Right. Let me stop it for now. Now I have in my hand a 47 ohm industry standard resistor. I'm about to implement the circuit we did earlier with this resistor. Just at this time, to not vary the speed because this is a fixed resistor. But let's insert it in and see what becomes of the circuit. This is 47 ohm. So again, so I'm done with this. I'm setting this one aside. 47 ohms. So let me power it up and see what becomes of the circuit. Notice how the LED glows dimly and the motor also turns slowly because I'm using 47 ohms. Assume that I have the resistance by connecting another 47 ohm in parallel to the circuit this way. Come on. Good. So now I have two 47 ohm resistors connected in parallel, which gives me an effective resistance of 23.5 ohms. Okay. So if I have several of these resistors connected in parallel, and I really insist on controlling the speed of the motor, then it means I'll need a rotary switch. A rotary switch produces some kind of stepping sounds when you turn it. It's something like a selector. So at a particular turn, it will select a particular resistance, and at a different turn, it will select a different resistance. So if you have several ports on the rotary switch and you connect as many resistors to such ports, then you can turn, by which way you have some kind of variable resistor. Okay, let me shut this down. Now, in our subsequent experiment, I'm going to take off these resistors, replace it with a jumper, and for purposes of simplicity, I want us to do away with the LED. I think the board is too cluttered. Let's get rid of this. Okay. Now, let's power it up and see. The motor spins almost instantly. Now, keep an eye on the direction of the motor. Do you see that it's turning to the right? Now, let me swap the terminals. So the positive terminal will now come here, and this one will now go there. And still it turns. Just at this time, it reverses direction. Okay. Let me reverse the terminals the way they were. We are reversing to the status quo ante. Okay, let me put it off in the interim. So assume for a moment that I want to program this DC motor to turn in only one direction, so that if somebody by error swap the terminals, the motor will not turn. We want it to turn in only one direction. We could employ the services of this diode. I want to put it here. So I'll take the jumper out. Notice that I can't put the diode here and here along the same line here. Notice I can't put it in this line and this line. When I do that, I'm practically shortening the diode. That is not what we want. So I'll shift this side to this line here, which has no link with this one. Good. Now let's power it up and see how it behaves. Since I've switched from here to here, so now this thing has to come here now. Good. The motor is off. Let's swap the terminals and see if it will turn. Yeah? Yeah. This one here. It does not turn. what is happening is that because the diode allows current to flow in only one direction, if I reverse the terminals, it blocks the current from flowing in the other direction. What it means is that the diode now presents itself as a very high resistance, almost infinite, so that only minority currents will flow, which are not enough to turn this device on. So the diode now presents itself as a very large impedance between the circuit because it is reverse bias, because I have not put the terminals on it properly. This is offering some protection to the circuit, especially if you have circuits which are very pole sensitive and will require positive to be attached to its positive terminal, negative to its negative terminal, and not the other way around. If you have a circuit like that and you don't protect it, you will just fry the device, destroy the device in a flash. So keep that in mind. Now this circuit that we have has a bit of a challenge. Maybe for now we have enough power to play with, but let's say we are operating on a very limited voltage supply, say 3 volts, and we have inserted the diode in series with this device. What it means is that this diode is robbing us of 0.7 volts, which is quite significant in the circumstances I have painted. So on that limitation, we say this design is not a very, very good design because it robs us of 0.7 volts. An alternative is to connect it in parallel to the DC motor. Let's try it and see what becomes of the circuit. This way. Oh, come on. Good. Now let's power it up and see. I think now I have to replace my jumper wire here and there. Over here, you notice that this motor is turning at a very slow pace because the motor turns at a very slow pace because the diode wants to stop it from moving because it is not properly biased. The terminals are not right, given the way I have turned the diode. Let's reverse it and see what becomes. Notice how the motor is turning now. Okay, I'm reversing the terminals. So positive comes here, negative goes there. And there you have it. It is operating at its full potential. This one is a better design because we're able to operate at our full voltage level. We are now robbed of 0.7 volts like we suffered in the earlier design. But you notice that something happens. When I reverse the terminals, it moves very slowly. It wants to stop it, but it cannot. There is a circumstance under which the diode with this configuration will stop the motor from turning. I want you to think of that and comment on it in the comment section. Under what circumstance would the diode stop the device from working with this configuration? And why is it not stopping now? Pass a comment in the comment section. I'd like to hear from you. That's your take-home assignment. Go and chew on it. Okay. Now, if all this confuse you, let me see if I can draw the circuit on the board for you. Our first design looked like this. We have our voltage source. So we had our LED. Set looking like this. And we had our variable resistor. Notice that this terminal was free. We had a motor configured in parallel with the with the LED. Connected in parallel this way. Our circuit didn't have a switch, but if you insist on one, it will look like this. So this is the portion where we swiped the cable around the graphite made variable resistor here. And the circuit is also representative of the one we implemented using the potentiometer. Okay. The ones involving the phase resistor looked like this. This way. This way. Come on. Yeah, this. Again, the motor will come. They were in parallel this way. Our power source was here. Move it back up a bit. Our power source. The phase resistors, if you recall, we had them in parallel. We started with one like this, and then when we added one in parallel, the circuit now looked this way. I think we used 47 ohm resistors. So here, this is the circuit. If you want to include a switch, again, it will look like this. Okay, now let's go to the one with the diode. So we had a motor only under the circumstances. And we connected a diode to it. To force it into only one direction and also offer protection. If it's a circuit that doesn't like to be reverse biased, this is one. And we said this one had a defect. So we revised and did something like this. So this one was a much better design because it did not rob us of 7 volts as it was in the case of the earlier design. But then the motor was turning small, and I'll give you an assignment to go and deal with that. And get your electronics books, read a little bit on potential dividers, Kirchhoff's voltage law, because that is what we are going to do in our next video. See you in the comment section in the next video. Do take care. Bye-bye.